Chapter 5, Section 1, the recording has begun for those who are not here. So I need your attention and quietly listening. Let's see what we have on our new chapter here. Perpendicular bisector is where we start with it. Now this combines two things that we are already familiar with. Perpendicular, what does that mean?
It means, that
they intersect, important that, perpendicular. 90-degree angles. Perpendicular, they intersect, forming a 90-degree angle. What is a bisector? And I'll say segment bisector. What's a segment bisector do? It goes through a segment, it crosses, bisector. What does a bisector do?
Line that bisects.
Cuts it in half. Two congruent parts. A bisector, we have two congruent parts. So, if I have a perpendicular bisector, it is doing both at the same time. This first figure, we have a bisector. It has made two congruent segments. It intersects at the midpoint, which happens to be point P on this segment. A perpendicular bisector is both perpendicular and bisecting, going through the midpoint, so we have two congruent segments. So we are going to look at something that is true when we have a perpendicular bisector of a segment. And that leads us to our first theorem for today, the perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, so we have a point that is on this perpendicular bisector. CD is the perpendicular bisector. Then this theorem says this point is equidistant from the endpoints of the segment. If I measure over to one endpoint, it's the same length as measuring over to the other endpoint, or we say it's equidistant. So if we know we have a perpendicular bisector and a point is on it, it's the same distance to either end. Equidistant from the endpoints. And then we take the converse. We reverse it. Now before we reverse it, let's make sure we get the order. First, we say we have to be on a perpendicular bisector. Then we know the point is equidistant from the endpoints. So if I reverse it, I say if a point is equidistant from the endpoints of a segment. So here is a point E. It happens to be the same distance from the endpoint. Then according to this theorem, it must be on the perpendicular bisector. If I draw this line, it would have to be a perpendicular bisector for point E to be equidistant from the endpoints. Same theorem and its converse, just change the order of those two things. So there's the first fact for today, perpendicular bisectors. If Wx is 25.3, now if you look right over here, you should recognize we have a perpendicular bisector. It's perpendicular, it bisects because these are congruent, so that point Y is a midpoint. Wx 25.3, 25.3, and Yz 22.4, 22.4. They want to know, and Wz 25.3, 25.3. They want us to find x2y. 22.4. I hope you have no trouble with that one. Now, the problem with what they did was what they do far too often is they put those little red marks there before they should. What they told you, or us, on this one is that W was equidistant from the endpoints by telling us they were both 25.3, which leads us to know it must be a perpendicular bisector. If M is the perpendicular bisector of XZ, so we have something new. If M is, line M, the perpendicular bisector of XZ. So now they actually are telling us what these marks mean. And W to Z is 14.9. W to Z, 14.9. Then they want to know, what is W to X? 14.9. So these are easy things as long as you remember the theorem, 22.4. That was our answer from right up there. If M is the perpendicular bisector, the last one down here, so the same thing of XZ, And Wx is 4a minus 15. 4a minus 15, and Wz is n plus 12. Did they switch letters? Those must be the same letters. A plus 12, I didn't read it. Those are both A's right over there. What do I know? The A's do what? Well, before I know what A equals, what do I know about 4a minus 15? It equals a plus 12. And then I can figure out what a equals. I'm going to subtract a, that would be 3a. I'm going to add 15, that would be 27. Divide by 3, and I can figure out what a equals. Next concept. Perpendicular bisector was the first concept. Next concept, concurrent lines. Concurrent lines are lines that all intersect in the same point. So you can have 3 or 4 or 5 or 6 or 7 concurrent lines. They all intersect in the same point. And that point they intersect is called the point of concurrency. Concurrent lines all intersect at the same place. We are going to begin to look at some special concurrent lines in triangles. And the very first one, that point of concurrency, we are going to have some lines that all intersect at that point right over there. And that point of concurrency has a special name called the circumcenter. We'll figure out why it has that name in just a second. The perpendicular bisectors of the triangle. Perpendicular bisectors. That means I need to take one side of the triangle, and here is a perpendicular bisector. Perpendicular, and it bisects. And we do that to all 3 sides. So this is a perpendicular bisector. This is a perpendicular bisector. They would all be concurrent on this point P. And that point, called the circumcenter, happens to be equidistant from the vertices. Same distance to all the vertices. That means this line, that distance, is the same as this line, which is the same as this line over here. Now that's the result of concurrent perpendicular bisectors. Those perpendicular bisectors all hit at a point. The result tells us that these distances to the vertices from that point are all the same. Now let me tell you, or you tell me, what shape would I get? Let's say I have a point P. What shape would I get if I went some distance out and put a point, and then went all possible points that are that same distance out from point P? What shape would that make? In a plane, it would make a circle, and I should have said in a plane. It would make a circle. If I did all the possible ones, we would have a circle when we are done. So that means back over here, if I have all these equidistances from that point P that reach these vertices, there should be a circle that would exactly hit on all the vertices. Question?
Have you ever heard that circle you point line just go around?
We'll discuss that later with you. Taken to the limit of a length of 0, yes, but you have to take a limit of that statement. Moving back to geometry, that's a good thing to think of. If I have a circle that hits all those vertices, and that circle is going around that triangle, what did we call it when Magellan went around the globe? Well, at least his expedition did. He got killed in the Philippines. Circumnavigation. He circumnavigated. He went around. That is why this is called the circumcenter, because it is going around that triangle. I'm going to illustrate which our favorite geometry software, GeoGebra. You got to play around with this sometime. It's really cool how it works. All I did was just drew some triangle, and then I created the perpendicular bisectors of all the sides. So this line is simply the perpendicular bisector of CD over here. Did the same thing with all 3 sides, and sure enough, they were concurrent at point D. Then I took the circle tool and I said, hey, make a circle, center D, and I drug it out to point C. Just hit one of these vertices. And if I hit one vertice, I also hit, finish that for me, all of them, because I am equidistant there. So I can take this triangle and I can change its shape. Does that circle always hit the vertices? Yeah. Is that point D always a concurrent point? Do they always hit in that point D? Yeah, no matter where I do it. Now, you notice that concurrent point may be inside the triangle. It could be right on the triangle, or that concurrent point could be outside the triangle. What kind of triangle do I have when the concurrent point is inside the triangle? An acute triangle. Every one of those angles is less than 90. What do you think the triangle is when I put it right on? See if I can get it right on.
Right.
It is a right triangle. This point C is going to be a right angle out there. If I put it outside, what kind? I've got an obtuse triangle. Turn the page in your book. See if I can make that go away. Not having much luck. Let's try the mouse to make it go away. There we go. Turn to the next page in your book. You see illustrated what we just discovered with our GeoGebra. The circumcenter can be on the interior, the exterior, or on a side of a triangle. And if it's on the interior, it's going to be an acute triangle. If it's on the exterior, it's going to be obtuse. And if it's right on the triangle, it's going to be a right triangle. Now, I put kind of dark black lines there. Remember, this point of concurrency is equidistant to all the vertices? That means that distance is the same as this distance, is the same as this distance, and that right triangle has been divided up into two little isosceles triangles. It wasn't originally an isosceles triangle, anything special other than a right triangle. But it has made a couple of little isosceles triangles, which look exactly like a problem on the test that you may remember. All right. Next thing, third topic that we cover today. Angle bisectors. What is an angle bisector? Splits it into two congruent angles. So if I have some angle and I draw the angle bisector right through the middle, I'm going to get two congruent angles out of that. So right over here, they've illustrated an angle bisector. BD is an angle bisector. And so we have two congruent angles that we have formed down there. If we take and study angle bisectors, we are going to discover a nice theorem with them. If I have an angle bisector, so a point is on the bisector of an angle. So we start with the fact that we know we have an angle bisector. So that is the thing we start with, angle bisector. This theorem says that that point is equidistant from the sides of the angle. Now we need to understand how we measure the distance between a line and a point. So here's a line, here is a point. How will I measure the distance from that point to that line? I could draw in all sorts of places. I could draw just like that. Do you think that would be considered the distance between the point and the line? No. Where do you think I should draw that? Perpendicular is where it should be drawn. That would be the shortest. Anything over here is a longer and longer distance, but if I go exactly perpendicular down here, then I have done the shortest distance. That is defined as the distance between a point and a line. It's the perpendicular distance. So, when they say over here, this point F on the angle bisector is equidistant from the sides, we know from that statement of the distance that those are perpendicular. What kind of little triangles have we just made then? Right triangles. They're right triangles. Second part, they turn it around. This first one, if a point is on the angle bisector, the result is it's equidistant from the sides. If I know I have a point that is equidistant from the sides of an angle. I know nothing else except I have a point hanging out there in the middle of an angle, but it's the same distance to each side. Then the conclusion is it must be on the angle bisector. So here we start with a point equidistant from the sides. Our conclusion, it's on that bisector of the angle. If angle BAC is 38, hopefully they didn't do too much. They didn't measure too much. BAC is 38. So BAC, that's the little angle right there, 38. And BC is 5. B to C is 5. So that distance is 5. D to C is 5. So they are telling us that this point C is the same distance to both sides. What do I know about point C? And don't tell me it's the same distance to both sides. That's what I just told you. What's our conclusion about point C? Well, a point can't bisect, but you're getting warm. It's on the angle bisector. If a point is the same distance from both sides of an angle, it is on the angle bisector. So when they say find the measure of angle DAC, DAC is this angle right there. What's the measure? 38. Easy math. We just have to understand what the theorem tells us. If angle BAC is 40, so BAC, same angle, it's now grown to 40. And DAC is 40. What do I know this line is if those are both 40? It's an angle bisector. And so what do I know about this point if it's on the angle bisector? It's equidistant from both sides. So if DC is 10, if this is 10, and they want us to figure out what BC is, no problem, we know it has to be exactly the same. It must be 10. So those were using both of the theorems, the original angle bisector theorem and its converse. If AC bisects angle DAB, AC bisects angle DAB, we know we are on an angle we have an angle bisector. And BC is 4x plus 8. BC, 4x plus 8. DC, 9x minus 7. What do I know about those two measures? They equal. So 4x plus 8 must equal 9x minus 7. Subtract my 4x is 5x. Add my 7 is 15. What is x? 3. Nice, easy math. We just need to remember that. Next thing that we are going to do to a triangle. Now let me back up, see if we can solidify what's in your mind, hopefully. We started with perpendicular bisectors, and we took a triangle, and we drew the three perpendicular bisectors of the sides, and they all met at one point, called a, what do we call a point when they all meet at a point? Oh, those of you remembered, it's a circumcenter. It's a concurrent point called the circumcenter. Why? There's a circle that goes around and exactly hits the vertices. Equidistance to the vertices makes a circle that hits those vertices. Now we learned about angle bisectors, and we are going to take the angle bisectors of a triangle. The angle bisectors of a triangle also intersect at a point. So this is an angle bisector, that's an angle bisector, this is an angle bisector. That's where we start with this picture. They all intersect at a point. That concurrent point is called the incenter. Now there's a clue here. The circumcenter was the center point of a circle that circumnavigated the triangle, that went around the triangle. What do you think the incenter is going to do? It's going to be a circle that is inside. And a circle is going to fit inside because that incenter point happens to be equidistant from the sides. If I go from that point and measure to the side, which would be perpendicular, because that's how we measure from the side, that length is the same as this length, is the same as this length. And if all those are the same lengths, I should be able to take a circle and put it right there where it exactly is inside that triangle. It's equidistant from the sides. We are going to see if that actually works, which of course it does because it was in our geometry book. So here I have, what did I draw originally? Angle bisectors. I drew angle bisectors originally. This line's an angle bisector of point C. Angle bisectors originally, so those are the original lines. They all connected at a point. They are concurrent at this point D, called the incenter. And that point then is the same distance to all the sides. So I just drew one line that went from D to E, which is perpendicular there, because that's how I measure the distance. And that became the center of my circle, and I hit at point E, and that circle exactly touches all the other sides. And if we measure D, oh, I didn't put that line, D to right here, that's also a radius. And this D to down there, that's a radius. I can move it off. That line is really not the... Oh, I did draw that one. Can I put this incenter outside of my triangle? No, you cannot put it. Can I put the incenter on the triangle? No, you cannot do it. Doesn't matter what kind of triangle. Obtuse triangle, right triangle, maybe about like that. Acute triangle, it's not going to go outside. It's always going to be inside, and that circle is always going to fit. Exactly. That's mesmerizing. See, you could do that Saturday night activities. That's a good idea. I need to remember that. All right. So let's see if we can remember some stuff about the incenter. P is the incenter. What does that mean? Point P is the incenter. That's lovely. But what does that tell us now? I can make a circle inside. That means KP what? Correct. There's the big deal for us. I know that this distance, this distance, this distance, they're all congruent. I also know what about LY? Tell me about LY. It's an angle bisector. It bisects angle Y out there. All of these. XJ is an angle bisector. ZK is an angle bisector. So if this is 20, I know, oh, that's not the angle. Sorry, that's the side. They give me angles. If that's 27, this is 27. If this is 31, this is 31. Now, I don't know any of these sides yet. Let's see what we can figure out, though. PK. How can I figure out P2K? I want somebody to have figured it out to tell me. Look at that, study that a minute. P2K. Almost thought I heard somebody start to whisper. I don't know.
Pythagorean Theorem.
Pythagorean Theorem is going to help us. If I come down here, I have a right triangle. I know I have a right triangle because from a point to a line, that's a right angle. So I know I have a right triangle here. And I can figure out this side of that triangle. How will that help me get PK? Because it's congruent to PK. It's the same length. So I can use the Pythagorean Theorem. I'm going to call that X for just a moment. And we are going to work at 4a right down here. I'll start you out. 12 squared. I know that's 144. Pythagorean Theorem. Plus, all right, the unknown, since I called it X, I'll stick with that letter, equals what? 20 squared. Now I'm going to rearrange this. I'm going to subtract the 12 squared. 20 squared minus 12 squared. And to get rid of the square, I have to, what's this called? Square root. Can you do that for me? What do you get? 20 squared is 400. 12 squared is 144, which is 56. Square root of 56. We need the square root. What do you get? 16, exactly. Square root of 56?
And 7.48.
7.48? All right, 7.48. So if that's 7.48, I know that PK must equal 7.48. We had to get there indirectly. We had to figure out, I know I have a right triangle, and I have two sides. I can get the third side, and that third side is congruent to KP. Measure of angle LZP. So let's find LZP. P. Where did P go? This angle right there. Now it's not 20, that's the length of the side. Think a minute. How can we do it? Don't necessarily tell me, oh, I know it's 13 degrees. How can we maybe figure it out? I agree. How can those other angles help us? We do want to look at those other angles. John?
This is just a shot in the dark, but if we take just like two big triangles at that base, right?
Uh-huh.
And the angle L, I think it is 90 degrees, and the one divided by y is 27. Couldn't you do what we need to get subtracting by 180 to get the angle Z?
I like how you are thinking. We know in triangles, well, they make 180 degrees, right? So, now I'm going to take that idea and tweak it just a little bit. Let's look at this big triangle. What's the measure of that angle up there? 62. What's the measure of this angle over here? 54. How did we get 54? 27 and 27. So what's left for this complete angle right there? Well, let's try it. 180 minus 54 minus 62. What's left for that whole angle? 64? And then, now that's not our answer, what will we have to do with that 64? Divide it by 2, because we wanted this little angle here. We know that's an angle bisector. 32 degrees. So, Mr. Hanson, good thinking. 180 degrees in a triangle is what we wanted to work from. Let's go to your books. Page 329. Am I reading that right? I need to reprint my thing. The ink was about gone. 329. Number 1. Says find each measure, and we see this lovely diagram. They want us to tell what x to w is. What has it been? I didn't quite hear. Oh, anybody? How much? It's going to be 12. Somebody tell me why. It's on a what? It's on a perpendicular bisector. That point X is on a perpendicular bisector. It's the same distance from both sides. That is why it is 12. That's the perpendicular bisector theorem. Number 2. A to C. What's the distance? It is how much? 14. It is 14. How do we get 14? 7 plus 7 is 14. I totally agree that 7 plus 7 is 14. How do you know that B to C is 14? I know we are on a perpendicular bisector because that B to A is the same as B to C. So that point B must be on a perpendicular bisector. If it's a bisector, those two have to be 7. Number 3. What can I set up?
10x minus 5 equals 7.
10x minus 5 equals 7x. Is it plus 1? 7x plus 1. I'm going to subtract 7x, which would give me 3x. Add 5, which gives you 6. Divide by 3, which gives you 2. Did they want to know x or something else?
They want to know L.
They wanted to know L to P. What do we do now? Substitute that x back in. I don't want to electrocute anybody. I'm not going to plug it in. I'm going to substitute. 10 times 2 minus 5. How much? 15. There's the answer, what we wanted. I know, that was a bad joke, but geometry teachers think they're hilarious. Number 4. 4 friends are passing out flyers at a mall food court. 3 of them take as many flyers as they can and position themselves as shown. So you can see friend A, friend B. Ben, are you with me? Thank you. And friend C. The 4th one keeps the supply of additional flyers. It says copy the position of points A, B, and C and then position the fourth friend at some point D so that she is the same distance from each of the other three friends. For number 4, I don't need to see the food court, but I do need to see friends A, B, and C. So make a diagram, it doesn't have to be to scale, that looks approximately like where friends A, B, and C are located. Now the question is, what is the name of the point that is equidistant from all three of those? We learned it today. So what? Is it the incenter or circumcenter? The circumcenter is the same distance from the, can you complete it? Vertices. That's what I want. This is just like having a triangle with your three lovely friends right over here. And we want to find the point that is equidistant from those vertices. How do we create the circumcenter or find that circumcenter point? From the, you can look in the book. It's not the test yet. It's a point of concurrency. The circumcenter is a point of concurrency, but how do I generate or create or find that circumcenter point?
Don't you go bisector 1, 2, 5?
What kind of bisector? We learned 2 bisectors today.
Angle bisector.
And there's the question, is it an angle bisector or what's the other kind? Or segment bisector, perpendicular bisector. Which one is it? It's the perpendicular bisectors. Find it in the book. It's the very first one. Very first one we did where they did the circumcenter. Those are perpendicular bisectors, right? So I'm going to let you sketch. We won't do a, what do we call those things when we do it with our compass?
Oh.
What blank all of a sudden? Construction. There we go. We won't do a construction on it. So if I do the perpendicular bisectors, I'm going to have a line. Is that about right? No, about right. You draw yours. See if you can draw ones that look like they, with your straight edge, look like they are going to be perpendicular bisectors. And when you do your perpendicular bisectors, they should all hit a point D. There's your friend from the perpendicular bisectors. Tell me how you did it. Perpendicular bisectors. That's how we located friend D. Dora the flyer hander-outer. Number 5. Well, Dora the Explorer was already taken, so it had something else. Number 5. Find each measure again. They want us to figure out what C2P is. Eight. We know it is 8 because that line BP is a what kind of ray or line? Well, same bisector, you've got a good chance of being right, but there are 2 kinds of bisectors. Angle bisectors, I didn't hear the first word, maybe. It's on an angle bisector, so it's equidistant from the sides of the triangle. Number 6, they want us to know angle WYZ.
23.
It's going to be 23, and the reason we know that one is they told us that the point W is equidistant from the sides. It's 4 both directions, so I know it has to be on the angle bisector. So that 23 is half of it. And on number 7, how will we do number 7? 2x plus 2 equals 4x minus 8. Because we can see that we are on an angle bisector, so those have to be equal distances. I'm going to subtract my 2x from 4, which makes 2x. I'm going to add my 8 to the 2, which makes 10. What is x? 5. And then what are we going to do with that x? We're trying to find q to m. We're going to substitute it into the 2x plus 2. What is q to m? 12. Number 8. Uh-oh. You know what I noticed we don't have? A proof. That's terrible, Gene. Number 8. Find JQ if Q is the incenter of triangle JLN. Incenters. So tell me about incenters. We need to know something about the incenter, otherwise we don't know what's going on.
The angle bisectors of the triangle are congruent.
They're formed by angle bisectors. I'll go with that. They're formed by angle bisectors. Draw out this diagram while you're thinking. Or maybe as you're looking back in the book. I don't know.
That's the angle bisectors.
What else about the incenter? It's formed by angle bisectors.
They're all equal.
I'm hearing this word equal, but I don't know what is equal. Incenters, they're formed by angle bisectors. Haven't gotten much past that yet.
And we're going to try to use, or well, the MQ to P, or congruent to P, congruent to KQ. So like,
Is it possible to answer my question? If we have an incenter, it is formed by angle bisectors. What do I know about incenters? I'm looking for the theorem. Find the theorem. What does it say about those incenters? Equidistant from the sides of the triangle. There's the thing that's important to us. They are equidistant from the sides. So this incenter Q, it's the same length as I go to the sides. My picture may not look like it, but as we go QK, P, and M, we are equidistant to all these sides. That's the key about incenters. So what do we have? 16.5 over here. Now you were to have been drawing as I was drawing and talking, and some of you were thinking. They are wanting us to figure out what length? J to Q? J to Q. Help me out. Yeah.
Are we going to have to draw a circle too?
No.
You know that PQ is 9 because it's congruent to QM. And
Now the PQ is 9, it's congruent to QM. And this is the hypotenuse of a right triangle. So what are we going to do? How are we going to find the hypotenuse?
Pythagorean Theorem.
Pythagorean Theorem. Pythagorean Theorem is what we are going to use. So we will say 9 squared plus 16.5 squared is going to equal, I'm going to call it x. That's what I'm looking for, x squared. So if I want x, I would just have to take the square root of this instead of squaring it over there. It's not going to be exact, I doubt. 18.79? Heard that twice. Must be right. 18.79 is the missing length. We did round it, 18.79. That's okay. Better not to round it too much. It's better to have extra decimals than too few decimals unless they have told us how far to round it. Page 329. Numbers 1 through 35.